Hello, madam.
Question 1. First, the length of the signal S1n is 61 sample. It is because the time index n goes from 0 to 16. Second, the signal is periodic. Its fundamental period or n value is 20 sample. The second signal S2n is also periodic, but its fundamental period is large at 200 sample. The difference is signal S1n move much faster, meanwhile signal S2n move slower, looks smoother, and has peak amplitude of 3.5.
For the question 2, we plotted a continuous time-damped complex signal. In figure 1, the real and imaginary parts are oscillating, but their amplitudes shrink over time. This proves the exponential damping effect of our system. In figure 2, the green line shows this smooth magnitude decay. Meanwhile, the pink phase line shows as sawtooth pattern. This is because the phase increases linearly, but MATLAB automatically wraps the angle between negative pi and pi.
So on task 3, there's 3 equations, which is h1, h2, and x. In MATLAB, we plot the graph using it, produce a discrete value graph with a standard function with negative x and take as their limit. Those graphs later used to complete the system using two functions, bn and yn. We using the convolution to work yn and x and bn was subplotted and produced this graph. The system order was reversed, which is bn equal to xn times h2n and yn equal to h2 bn times h1n. When we compare those graphs, bn are different since it represents different halfway points through distinct filter, while yn does remain the same thanks to the commutative properties, which is ax times b, a times b is equal to b times x.
Question 4. We convert a triangular path with casual then sinusoidal signal. In MATLAB, we use a precise time resolution of dt equal to 0.01 and scale the ground function to correctly approximate the continuous integration. To validate this, we perform a manual piecewise derivation. Because the triangle change slope, we split the integration into 4 time dependent boundary case. First is zero overlap, then the rising edge, the falling edge, and finally the pure decay. Our analytical methods perfectly match the simulation. This proves that the triangular pulse acts as a smoothing filter, spreading the output duration across the combined length of both inputs.
For question 5, we analyze an ideal low-pass filter. Part A shows its since impulse response. In part B, we filter an input signal. The output becomes smoother and its peak shifts to the t equals 3, proving the filter's 3-second delay. Finally, in part C, we input a square wave map of 20 harmonics. The filter blocks all highest frequencies. As a result, the square wave magically transforms into a single smooth delay sine wave.
Now let's move to question 6. Using the prodigy fraction method, we find the context A equal 5/3, B equal 2/3, C equal 2/3. This given is the impulse response ratio. The first system is unstable. It is because it has a e power 2t term that row of infinity, and the ROC does not touch the imaginary axis. Finally, for part C, the new manual transfer function is HS equal 1/s power 3 plus 7s power 2 plus 16s plus 12. MATLAB show that all the poles are on the left side of S plane at S equal -3 and S equal -2. Therefore, this second system is completely stable.